Hello, good afternoon, everyone. Let's go ahead and get started. Just as a quick reminder, the homeworks are going to be due today at midnight, so make sure to submit that before the end of the day. And the project proposals are going to be due on the end of the day on Friday, so please make sure to submit those as well by the end of the week. And I received, like I said before, please do reach out to me about your project topic before you submit the proposal, just so that I can make sure it's appropriate for the class and that the scoping of it is correct. I have received project inquiries from most of the students, but if you haven't so far, please make sure to do so before submitting the proposal on Friday. Yeah, if there are no questions about either the project or about the homework, we'll move on to today's lecture. Okay, so today we're going to be talking about simple approaches and models for understanding aggregate system models for both energy and transportation. Okay, this kind of continues some of the common themes from last lecture, where we were mainly focused on doing forecasts of technology, but a lot of what folks are doing in this space also looks at impacts at a sort of system level. And so one of the most common forecast to think about is the historical CO2 emissions. And again, these can be historical emissions, can be used to project future emissions. This sort of falls in line with the thought about using past data to try and predict or project future data. And so that's what we'll be sort of focusing on today. But specifically looking at things about energy use, things about emissions. So what simple approaches can we use to project and analyze future use and greenhouse gas emissions? So before I dive into these, we will talk about later on in the class sort of more bottom-up ways and complex methods that really sort of break down into detail specific sectors or industries to help arrive at these sort of answers. But at the same time, one of the things to keep in mind with some of the simple models that we'll be going over today is that oftentimes when you delve into a lot more detail in complicated or complex models, there can be a lot of uncertainty that drives a lot of those results. And so with some of these simple models, it's nice because your accuracy doesn't really suffer. And so you can actually arrive at fairly accurate numbers, even if the sort of precision about specific details is not the same as in more complex models. There's a lot to be said about sort of taking a simple approach to get at some of these impacts. Okay, and so what we'll be looking at today: energy demand projection methods, greenhouse gas drivers in different energy use sectors, a whole set of decomposition methods, which we'll cover, and actually several of these below, like the Kaya emissions projections, the 80 and 50. These are examples of decomposition methods that sort of simplify your system into really sort of straightforward numbers and breakdown of parts of the system. And then we'll talk about mitigation options, which is another technique that's commonly used to show impacts in a really discrete way that's useful for example, showing policymakers and really being understandable about what specific outcomes can result from any sort of intervention process. And then lastly, we'll talk about accounting and stock turnover models. And this is actually probably most closely related to some of the diffusion models that we were talking about before, in the sense that we'll be talking about specific technology turnovers. Okay. So the first set of sort of system-wide models that we'll be talking about are the simplest options. So again, this may look somewhat familiar. This is a extrapolation using simple growth rates. And so this equation actually looks pretty similar to some of the stuff that we were doing in the economics and financing lecture, where we're talking about doing present values or future values using discount rates or interest rates. It's the same sort of concept, right? And so as your R over here increases in size every year, this factor is going to be getting larger and larger. And so this sort of growth rate is a way of representing some sort of regularized growth pattern that represents kind of what you would see on average. And so this is the type of thing that you might see for like annual GDP growth or annual population growth, or in this case, annual growth in energy demand, right? And so this really is kind of a top-down approach, right? Because we are not really talking about any specific factors that are like increasing energy demand. It's not like I am figuring out that, you know, the electricity associated with watching TV is going up because, you know, TV shows are becoming more popular, or you know, like movie theaters aren't really in vogue anymore because of coronavirus, right? And so this doesn't really care about any of the explanatory factors that are going into changes in energy demand. It's just looking at the trends, figuring out like a growth rate, and then projecting outwards from there. And so this is useful really for doing like baselines and thinking about trends that continue from the past. But where you're probably going to run into some difficulties, right, is if there are any like interventions or large differences that are happening over a period of time that you don't really observe historically. So for example, like this wouldn't do a really good job of understanding the energy demand that got impacted from coronavirus, right? Because you don't really have those underlying factors. On the other hand, you know, you could build a super complex model to figure out energy demand, and you could come up with a really sort of similar answer as this, especially if you don't have a lot of external factors that are deviating energy demand from historical norms. And so there is actually a lot of value in being able to do something as simple as this. Um, okay, so the next example is where we start to think about, okay, what does go into energy demand? And so this is where you may start to introduce the ability of this equation to factor in certain certain aspects that could change the energy demand over time. And so in this particular example, we're breaking down the energy demand into GDP times energy intensity. In other words, how much energy is consumed on average per sort of dollar of GDP. And so this suffers from a lot of the same sets of drawbacks that I was talking about in the earlier, in the equation before, but it's starting to introduce some details that you could possibly manipulate. And when I think about this simple option versus a really complex option, you are talking about essentially taking this step to the extreme, right? At the end of the day, you want to figure out the energy demand, and you're going to break it down into these factors that affect it. And you can go into a whole lot of detail about, what it is composed of. But this is, right, just one step removed from our sort of simplest option. Yeah, and so in this case, again, it's just an analysis of trends in GDP and in energy intensity. Generally, this type of equation does a pretty good job. It doesn't consider technologies explicitly, right? And so you could figure out that technologies in general are getting more energy efficient. And so that would then in turn influence your second term here about your energy intensity. So as you transition from like gas cars to electric cars, or as you transition from fossil fuel generators to renewables, you could capture that by figuring out how that changes your energy intensity, your energy consumption per dollar of GDP. Okay, and so we can continue to sort of break this down. So econometric models are often more sophisticated versions of these simpler approaches. And so we're continuing to sort of layer in a little bit of extra complexity into these models. And so this is still, this sort of extrapolation method, but now you've got some elasticities in your alpha and beta associated with the actual income and energy price. And so in this way, we can use historical data to estimate the changes in demand. And so that historical data, right, are your explanatory variables y and p. Once again, these sort of high-level models ignore the structure of energy demands, right? So the thing that is actually causing the change. And because of that, again, this approach is going to sort of break down when you're thinking about longer term structural changes or policy changes that will influence your system in ways that we haven't observed in the past. And so again, useful for baseline scenarios, for BAU scenarios. This stands for business as usual, if you've never heard of this. And business as usual type scenarios are nice ways of setting baseline, because it really just means that you don't really have any intervention or changes, structural changes or policy changes that would affect the system in ways that we haven't seen them before. Okay. So extrapolating trends. So the first two sort of classes of projections assumes that changes in the future look similar to changes in the past. And again, that's why we can make these simplifying assumptions, that because we have so much sort of information to go off of and to calibrate these sort of average trends, that you can have a fairly good picture of what your future looks like in the absence of any intervention. So when you do want to start to explore the influence of certain mechanisms on your outcome, the sort of most important thing is to find the right parameter to extrapolate. And so just as an example, to reiterate with, for example, this equation, right, when I was talking about like changing a technology that influences efficiency, right, we know that that's going to affect the second parameter and maybe not the first one. And so that's really what I mean, is that you need to essentially figure out, you know, what it is that's influencing the model, and then change that that specific parameter. Okay, so strengths and weaknesses. I think I've been sort of harping on this enough. Very simple approach, allows you to do baselines, but it's not going to let you figure out systemic changes in your energy or your transportation system. Okay, and so those were some top-down. Bottom-up forecasts often start at a really sort of higher level of detail. So thinking about engineering or end-use models to explicitly consider changes in technology and service levels. So this particular equation is thinking about the same outcome, energy demand, but it's looking at all of these decomposed systems. So you may have a specific end use, and then the number of people who use that, the fraction the total number of people, the fraction of those people who actually use that particular end use, how much it gets used, and then the energy intensity. And so in this case, in order to build up to your like total system, if I want to be equivalent to what I was saying with the top-down system, your I needs to encompass basically every observable end use technology. And so these bottom-up methods are nice in that you can really get into detail about every specific item that influences your end use. On the other hand, they can be really difficult because you need, in order to get the sort of total energy, you need to account for basically everything in the system individually. And so in this example, you know, this could be like lighting, could be transportation, which probably breaks down into even a whole bunch of other things, like, you know, car transport, bus transport, airplanes, and all of that would have to get integrated into this system in order to get to get at your total energy demand. So the nice thing about this is that you get to explicitly identify the demand across all of the different sectors. And if I want to specifically change one technology, I can do that here, right? I can go into the correct eye and figure out how each of these are going to change. Like if I were to if I were to increase the number of people who are using electric vehicles, then you could change your fraction of customers, right, who are using that technology. If I wanted to improve the fuel efficiency of a vehicle, then I could affect the energy intensity, which equivalent to the efficiency. If I wanted people to drive less, right, then I could affect the use of service. And so that is just for I equals your passenger cars. You could do the same for lighting. You could do the same for anything else, right? And these type of changes would be very difficult to do in the top-down model because they're specific and they're not. They're only affecting sort of a portion of the aggregate. So these types of models are really nice for looking at changes in specific technologies. Okay, and so the bottom-up approaches let you understand demand and emissions impacts at a much more disaggregate level. It gives you a nice representation of the energy use within every sector. And you can even start to incorporate larger systemic changes, such as policies that affect specific technologies. Weaknesses, so besides the ones that I was mentioning earlier, that you essentially have to find, if you want sort of a system-wide impact, you have to accommodate all of the technologies in that system. In here, it's also subject to some biases about how you think changes in any one of those parameters could get affected for a technology. And then because, as you see in this original equation, because like pricing is not explicitly accounted for in this formulation of a bottom-up model, which might affect something like fraction of customers, or it could even influence the use of the service. Because those things aren't included, then that's another source of bias that could be introduced, that would be tied to whatever sort of the forecaster believes about how those parameters might change in the future, independent of pricing and economics. Okay, so I wanted to show a nice sort of real world example of some of these higher level approaches, and some caveats to think about related to them. And so here, let's say we wanted to make projections for fuel economy. One of the really important things to think about is that if you do one of the top-down approaches where we look at trends in something like fuel economy, this is again to sort of illustrate the point that you may do a good job on the trends, but but you could also miss some underlying effects and drivers of these trends. So this this chart here is a plot of the average on-road fuel efficiency for vehicles sold in a whole bunch of different countries. You'll note that the United States is here in the red, and it's sort of decreasing over time. And you can see the same thing over here, but this is increasing, and the reason for that is because this is liters per kilometer, whereas this is miles per gallon, and so they're inversely being portrayed. Starting in the 70s, you can see in both charts a improvement in overall fuel efficiency that goes all the way till about sort of 1990. And so you can see that here as well, this improvement, and then it sort of flattens out for a long period of time. And so when we think about this trend, then you basically say, well, okay, so fuel efficiency has been improving for a small period of time, and then it sort of flattened out. But when we look at some of the underlying drivers for fuel economy, what are the things that can affect the efficiency of the vehicle? So you've got the weight, power, and also design of the transmission are all parameters that can affect fuel efficiency. And these things are shaped by both policy as well as consumer preferences. So going back to here, later on in the course, we'll be talking about one of the sort of large-scale transportation policies called the CAFE standards, which is the Corporate Average Fuel Economy Standards in the United States, which are requirements for automakers to build cars of a certain fuel efficiency. And that was first introduced in the 1970s, sort of following the passage of the US Clean Air Act. And so the main thing there was they wanted to make cars pollute less and to reduce reliance on foreign oil, because this is sort of following in the footsteps of the oil crisis that happened in the United States in the 1970s. And so there was, for a period of time, a market improvement, but then the policy itself ended up having a requirement that didn't improve for the span of about 20 years. And so you can see that really clearly here. And so what ended up happening is that because the stringency of those policies was no longer binding for automakers, they were able to put their technology improvements into other aspects of the vehicle while keeping the fuel efficiency sort of relatively flat. And so what were those things that they were improving? So from a weight perspective, they started selling sort of bigger and bigger cars, which is something that consumers liked. They started changing towards a lot more proportion of automatic transmissions. And then this 0 to 60 time is related to the power of the engine, or acceleration, right? So how long does it take you to get to 60 miles per hour? And so as this number decreases, it means the car accelerates faster. And so the sort of fascinating thing about this is that, in effect, the efficiency was actually improving, but you also have a bunch of factors that were sort of counterbalancing some of those technological improvements in the fuel efficiency. And again, this is strongly shaped by the fact that policy no longer required the fuel efficiency to improve, and because consumers wanted bigger cars and faster cars. When we look at efficiency, or in this case, fuel consumption per unit weight, you can see that over time, there's a very nice trend that shows that cars really are getting more efficient as you control for weight, and that they are also getting more efficient when you control for power or acceleration. And so engines tend to be less efficient the further they are from their sort of maximum power point. And so here, this sort of nicely demonstrates that that as sort of the acceleration was improving as an attribute for vehicles back in the 80s and 90s, at the same time, you had sort of lower fuel consumption associated with those higher power. So future fuel economy standards. So this is an estimate of potential for increasing fuel economy, assuming that other attributes are not improved. And so this is actually something that you can do with the previous data, where we can go back and say, what happens if I were to flatten my acceleration or flatten the weight and continue the same trend for fuel efficiency improvements, and you know, that is one way that you could really simply extrapolate existing trends and sort of maybe say, for the sake of changes in policy or changes in consumer preference, you know, how that would affect your fuel intensity outcomes. And so this kind of extends from your really simple model to controlling for certain parameters that are affecting your outcomes, such as weight and transmission and power. Okay, any questions here? Okay, so moving on. This is a nice little chart that I like to show as sort of a warning for forecasting. So this is a chart of total CO2 emissions coming from the United States. And this is published from the Annual Energy Outlook, which is a report that the Energy Information Agency publishes every year. It comes from this really large-scale energy system model, and it is if you haven't seen it before, it's actually a really nice repository for data about what the government thinks the future of the energy system is going to look like. And we'll actually talk a little bit about this, about the EIA annual energy outlook model in another class. But so this is a, I believe this is from the 2017, the 2017 annual energy outlook. And so these are the emissions sort of over time. And one of the things that the AO does is it provides forecasts of what it expects future outcomes are going to be for a whole host of things. And in this case, they're providing annual projections for emissions. And so what we did was we actually went back and looked at their projections back when in 2000. So imagine if you sort of cut away the black line here, then we're only allowed to look at everything before. You can do a pretty sort of simple extrapolation, and in fact, this is what they did from each of these points as you move further and further. And so a lot of these lines end up becoming fairly inaccurate because there were sort of larger systemic changes that happened in the energy economy sector. And so you could just kind of see how off those projections are when you do subject your system to large scale changes that aren't really going to be well captured by the historical patterns. And we can see that really sort of clearly here, right? A lot of those, a lot of the sort of systemic changes have to do with the big economic downturn that happened in 2008, as well as shale gas adoption that sort of transitioned us away from a coal-dominated electric sector to a more natural gas-dominated electric sector. And so that's why a lot of these projections are sort of really sort of quote unquote wrong, but they're only wrong in the sense that they didn't account for these large scale changes. Had we continued on baseline, it is pretty likely that we would be on that sort of similar trajectory.
So are these their annual energy outlooks? It's purely based on historical data?
Not only on, well, so everything's calibrated to historical data, but the model itself is this fairly sort of complex model that spans the entire economy, and so there are definitely other things that sort of go into this, but even when you get into some of that nitty-gritty detail, it's hard to account for these larger systemic changes, and so that's why their numbers are really off. But yeah, everything, the foundation of what the EIA AEO does is based off of is based off of historical patterns. Yeah. Yeah, so this is one of the projections or forecasts coming from the AEO. These are forecasts of imports of natural gas, and prior to the discovery of shale gas, a lot of those projections basically were saying, hey, we're going to need a lot of imports, and as time goes on, more and more shale gas resources became available, and so that sort of shifted the projections downwards. And so the AO 2014 was basically flat, right, in its projections. So it's awfully hard to make predictions, especially about the future. And so this is kind of one of the central tenets of a lot of these forecast models, is that you're often going to get it wrong, but there can still be value in understanding the system. So when you think about sort of these retroactive analyses that point out a lot of the flaws in models that project out into the future, I think one thing that is often missing from those discussions is the value of sort of making some of those forecasts, because they can still be helpful to inform stakeholders and policymakers about what might happen, right? If you continued in like a business as usual scenario. So if I were to take a step back and think about climate change, and you think about a lot of the sort of energy models or transportation models or these sort of larger scale climate change models that think about these projections of the future and are likely going to be wrong. Like if we didn't make those models in the first place to demonstrate some of the like negative impacts, then maybe you wouldn't get some of those systemic changes that are trying to mitigate climate change in the first place. So just because these forecasts are not representing what happens in reality doesn't make the models sort of quote unquote useless. Yeah, and so that really sort of brings us to this idea about scenarios, which is this really high level way of demonstrating sort of possible outcomes to specific assumptions, and that's where I think there's really a lot of value in doing a lot of these modeling exercises, is being able to demonstrate to the right stakeholders the sort of possible outcomes or range of outcomes in any sort of decision-making process. I really like this sort of diagram for sort of describing qualitatively what a scenario is, right? So you can have some story about what you think the future might look like, and if you inject into it like some quantitative rigor, like models that really describe how reality can actually be affected by specific assumptions, that is where you get into this territory about being able to both illustrate these high-level ideas and options, but also include rigorous analysis and evaluation. And so this little sort of chart shows you a couple examples of relevant sort of stories and models, and where uncertainty becomes really dominant, in which case some of the models that you do, it often makes a lot more sense to think about these in terms of scenarios, because you don't know even how the inputs should be necessarily treated. I mean, you can't treat them sort of statically. Okay, so with scenarios, these really do have to be coming from some kind of quantitatively modeled analysis that can be sort of rigorously evaluated to both understand how the assumptions drive your outcomes, but also whether the sort of system that you're describing via the model makes sense. When you have multiple scenarios, it makes it possible to examine different futures, right? So this means that, even if you don't believe, one set of assumptions that leads to a specific type of outcome, you could plug in like a different set of assumptions and look at a different outcome. And so this is a nice way of being able to look at multiple outcomes with one particular model. You might also do this to examine like different sets of impacts. So like if a policymaker wants to if I want to do X or Y or Z and which one leads to the lowest emissions, right? So this is a nice way to do that. It enables the audience to think about a bunch of different possibilities, and that's really up to the modeler to highlight all of these possible forecasting ideas. It can capture structural changes within the model. So as long as your model has the ability to capture that structural change, you can introduce it as one of the parameters that you'd be varying to look at a particular scenario. And then the development of a particular scenario is part science, part art. It requires the modeler to think about what sorts of things that I might want to explore. And so if I go into any particular model, you could have, for example, you could literally have like 1 million different variables. And it wouldn't really make sense to try and vary all of them, because you may end up with like a trillion different outcomes, right, that could all point to different futures. But if you want to sort of focus on a particular driver where you can have a lot more emphasis on one particular scenario being driven by one particular parameter or set of parameters, that can be really helpful, especially in really targeted regulation or policy. Yeah, and so there's this paper by Ganadin and Kumi, which I think is a really nice demonstration of this. I'll link this as reading in the on Canvas if anyone's interested. This is a paper here, and this I think this is a nice sort of example of how these authors came up with a whole set of alternative scenarios that are really different and that can highlight sort of very different outcomes based on what the authors based on a series of really sort of different scenario outcomes. And just to give kind of like a little illustration of what they did, and sort of this is not exactly the same, but sort of in the same vein. You can actually construct these high-level scenarios where you tune your parameters to really highlight like a vision of a potential future. And so in this case, you might think of a really sort of optimistic scenario case where a lot of the things, a lot of the parameters are based off of these this perception that people get smarter about things like climate change and energy efficiency, right? And so in this case, people think about commuting via like active transport more or through cleaner modes of transit. They changed to alternative fuel vehicles. And right, they eat sort of local sustainable food. And so that is one sort of vision in which you can, take this idea and sort of extend it into your model where you think really optimistically about the outcome. And so this slide is kind of like the story, right? And then what goes into the model is driven by the sort of backstory. You could do the same thing for a more sort of pessimistic view of the world. So they call this the sort of state of fear. You hoard gasoline. You think about wasteful use or the use of goods and services is inefficient from like an energy perspective. You get a bunch of land sprawl, drive fuel inefficient vehicles. So again, this is kind of a design of a story that can then inform how you structure your model assumptions. You could have something that sort of just falls in baseline, and so this is a continuation of, for example, trends that might be happening now. And so going back to thinking about the models themselves, right? The models themselves are just describing relationships between technologies, how they use energy, how much energy is consumed in a particular end use. But the way that you decide how those actual values get filled out in the future is based off of like a story that you construct about the future. And so these narratives are really kind of the thing that drive your assumptions about what's going to happen in the world in the future. And it's a combination of both these stories and the modeling rigor that leads you to understanding the sort of impacts of telling this type of story. Okay. So this is a nice spot to take a little bit of a break. So let's break for 5 minutes and then I'll continue onwards. And then if anyone wants to chat about any of this stuff over the next couple minutes, I am open. All right, let's continue onwards after our break. So right now we'll be talking about a couple decomposition methods that break down from the sort of first energy energy demand calculation that we were showing. So probably the most famous one is known as the Kaya equation. So this is trying to understand drivers for greenhouse gas emissions, sort of in an aggregate sense. So what are some factors that determine greenhouse gas emissions? So you can kind of think about this in your own life. What are some key choices and decisions that influence your energy use and carbon footprint? And so, if I were to think of that sort of on my own, key choices and decisions, those would probably be, okay, how do I get myself from point A to point B? So transportation, if I'm driving or if I'm biking or I'm walking. So what are some other things? What I decide to eat, right? And so that's going to have some impact based off of what food it is, what's the energy and emissions associated with that particular food, and sort of all the upstream effects. Other key choices, so how much I use entertainment devices, so like TV, computer, these things consume energy, and those all lead to upstream emissions. Okay, and so when we think about all of these factors, you can generalize them. Okay, and so if we want to think about beyond just the individual, we need to think about sort of the whole population. So a lot of the stuff that I was talking about in terms of like choices and decisions, that is really related to activity and consumption. So these are things like amount of driving or flying, size of homes, transportation mode. And so you can think about all of these activities and consumptions and sort of average it for the typical sort of person. And in that way, with both the population and all the activities, and coupled with the energy intensity, so the amount of energy consumed for all of those activities, then I can get at the sort of total energy demand. And then the sort of final step is the conversion to GHG emissions, which is your carbon intensity. And so how carbon intensive is any particular activity or consumption process. So the Kaya identity, the Kaya equation, is a form of multiplicative decomposition. It breaks down your emissions into a product of several drivers. And so again, if you have the population, the GDP per capita, which represents your activity, the energy intensity as energy per unit of economic activity, times the carbon intensity. And so this comes almost directly as an extension of that first equation that we were showing, which just does, right, where I had energy here, and then I didn't have this last term. And so by including that, I can get to my greenhouse gas emissions. And again, you can sort of see what happens here, right? The population cancels out with the per capita, cancels out with the GDP, and then energy cancels out, and then you finally get GHGs at the end. So this framework is a specific application of the IPAT equation. So we'll talk about that right now. And so this is looking at pollution impacts. And this originated back in the early 1970s from this famous paper, Ehrlich and Holdren. And I always forget to check this, but I'm fairly certain this Holdren is the John Holdren from who headed the science office under Obama. And so this looks at pollution, or so at a higher level. The IPAT stands for impact is equal to population times affluence times technology, and this was applied to look at pollution impacts. So pollution is equal to population times consumption per capita times pollution per production. So it's a nice sort of simple approach that shows how different parts of this equation contribute to elements of environmental problems. The main focus originally was to think about population and consumption. And again, it's a nice sort of qualitative example of figuring out the drivers for pollution. Originally, technology was viewed as the main problem, sort of the source of the environmental damage. And so this last term here was really sort of pointed out to be the sort of cause of some of the issues, but that has sort of since shifted in now thinking about this term as a lever in which you can help to improve or decrease the impacts from pollution. Okay, and so let's talk a little bit about the implications of this Kaya identity. Population and activity are these socioeconomic parameters, right? And so GDP per capita is a measure of economic activity per person. And we tend to think that that GDP per capita increasing is a good thing, right? In economics, that means that that essentially means that people are wealthier and therefore better off. You have more utility. And so one of the really even in sort of a simplistic framework like the Kaya identity, one of the fundamental things that it started to point out is that, hey, this might not necessarily be a good thing always, because, okay, yeah, you are improving, wealth of your population, but at the same time, right, you are, like, this is directly a factor that's increasing your GHGs. And so as wealth increases, you also have GHG increasing. And so that's going to become relevant when we think about policy levers. Okay, so Energy intensity and carbon intensity are socio-technological parameters. So energy intensity depends on the type of consumption or production and energy technologies within an economy. And so there's this thought about, trade-offs between energy intensity. So you might think like this one simple example is if I were thinking of, if you were to break this down into like different transport modes, right? The energy intensity coming from specific technologies within that sector may be really different depending on how you decide to shift towards one transport mode. And then lastly, carbon intensity. So that depends on your primary energy resources used in the economy. And so you can also shift the sources of energy which affect, which in turn are affected by the carbon intensity associated with that specific energy resource. There's that, or you can actually make the process itself more efficient, in which you can reduce the CI associated with your particular technology. Okay, and so even this sort of basic understanding reveals a lot about, hey, what sort of policy levers and mechanisms can we take to address the broader GHG issue, right? I can reduce activity or consumption, right? And you can do this by reducing the population, which may be a little bit less feasible, but you can also do this by reducing your GDP per capita. And so that is one of the like controversial parts where you're sort of directly in conflict with a desire to have like a stronger economy, right? Basically increasing your GDP per capita for improving wealth. I can improve energy conversion and end use efficiency. And so this is your energy intensity. And so if you make like a gas car more efficient, for example, that's going to help with the energy intensity. And so this is a lever that really focuses on efficiency of your end use. And then lastly, fuel switching. And so you can have policies that sort of promote renewables, for example, as opposed to fossil fuel plants. And so these are all sort of these high level policy mechanisms that end up getting derived from a really sort of simple structure. There are a bunch of different calculators that you can use to look at this. So this is a particular example where you can do projections of each of your different Kaya parameters. What happens if population, economic output are increasing, but energy and carbon intensity are decreasing? Like how much would you have to improve your intensities in different ways to overcome your population or economic output benefits. And so I've provided a link here. You can take a look at this. This is a really sort of simple example where you can mess around with different parts of your Kaya identity. So let's say I wanted to improve the energy intensity. Oops, what's going on here? I don't know why it's switching to this. Okay, but okay, well, let's say we want to change the GDP per capita when it's growing at 1% and I have a plateau of 9 billion people. Oh, it's okay, I see. That's the difference, the different each of the different parameters are located in the box under it. Okay, and so if I wanted to change these, you can see what the overall impact on greenhouse gas emissions are, sort of starting from all of these years and moving forward. So let's say I wanted to say there's like a population of 10 billion people at the maximum. Let's say your economy grows at 2%. You can see how this is going to lead to some amount of total emissions by, or annual emissions by 2100. So what would it take for me to flatten this curve? Let's suppose the rate of change were like 5%, 5%. So you can mess around with this calculator a little bit and sort of get at your end emissions impacts as you affect different parts of your Kaya identity. And the slide here just shows a couple sort of different examples of parameters that are getting messed around with in the Kaya calculator. Global averages versus regional disaggregation. So global average values can be useful, but if you want to do some disaggregation, that's still possible, where you now break these Kaya identity measures down by this index I, which is for each of your different regions. And so this is an example of application of your Kaya identity across a bunch of different countries and regions. And this comes out of a famous paper in PNAS. And the nice thing about this, you can really see how there's a lot of heterogeneity, right? There are a lot of different sort of trends and patterns that are coming out of different regions because of the heterogeneity that you would not be able to see very well if you just averaged everything together. Okay, and so I'll quickly sort of cover a couple other versions of decomposition methods that really sort of fall in line with this IPAT and Kaya identity. So there are a bunch of sector-specific decompositions, and we'll talk about, well, we're going to actually focus on some of the transportation ones, which I'm most familiar with. But there are a couple other examples as well. This is from an 80 and 50 decomposition model. This is from the actual report, which is a fairly well-known report that actually came out of Davis in the 2000s. So industrial ecology has this decomposition. This looks pretty familiar, right, as the IPAT equation. This looks at focus on extraction, production, and use of materials. So this is material density, dissipation factor. H is the hazard factor. So I'm not going to go, a whole bunch into detail about this, but this is done by a couple authors here. You can check out the paper if you like. This is just another example of an application of the IPAT method. This ASIF decomposition, similar type of thing. I'm a little bit more familiar with this because of its application in the transport sector. So this is G equals ASIF, so that it's called the ASIF decomposition. So A is total transport activity, S is the modal structure, so that's the mode share. So like, what happens if you're at like 80% cars, 10% buses, 10% trains, that sort of thing. Each of those modes has an energy intensity So there's an efficiency in terms of fuel associated with that mode, and then a fuel carbon content. So the G is going to give you your greenhouse gases associated with each of these things. And so really this is kind of like a restructured Kaya or IPAT equation with each of these parameters being specific to parameters that are in the transport sector. And you can actually see you can actually end up getting a lot of sort of nice details that's help inform even the inputs that go into this equation. The 80 and 50 emissions analysis framework, another decomposition method. So this is using the Kaya identity, but with transportation sector specific items. And so transport intensity instead of your GDP per capita, your energy intensity that is in terms of energy consumed per mile, and then carbon intensity associated with the sort of fuel use for that transport. So you can calculate, so the way that they did this 80 and 50, and I should note, the report is called 80 and 50 because it's analyzing the AB32 scenario of reducing California's total emissions by 80% by 2050, or 80% down to 80% below 1990 levels in 2050. So 80 and 50 is kind of the shortcut for this. And so this is a nice way that was employed to understand how we could leverage each of these factors, the T, E, and the C, to meet 80% reduction. Like, what are the options to get down to 80%? And I'll give kind of a quick rundown of some of their approaches and results. So for any mitigation option, or for every mitigation option, there were two essential questions, right? So how much does it get used, and how much better is it than the current option? And so you have to evaluate basically all the potential technologies. And it was a really sort of interesting exercise that they performed, in that one of the things that they showed was that, like, hey, these values actually have to be really sort of good in order to get to your ultimate target of 80 and 50. And one of the things that this highlights that I hope you guys take away from this is that, you know, I can do a whole bunch of complex modeling and really detailed sort of examination to figure out how hard it is to get at to reach this particular goal, right? But I can do this sort of simpler, high level approach to basically come to the same conclusion. And so the report was nice in that it highlighted a lot of these issues in a really straightforward, simple way. And so these particular scenarios, I highlight these, show, okay, simplicity and transparency, which is really important because to some stakeholders, like, you could make this complex model that really ends up being a black box and we don't really kind of know what goes into it. But in this case, it's really obvious. And then the other thing is that you don't need a lot of complex modeling to understand that that you could get to this particular outcome with a diverse set of options. And so, you know, even though you have a fairly simplified representation of your transport subsectors, light duty, heavy duty, aviation, rail, all of these things, there are a whole diverse set of ways you could reach your goals, given all of those sort of subsectors. Okay, So let's continue onwards. Stabilization wedges. So this is kind of building off a little bit on the outcomes of that 80 and 50 study. So you may have this question about, okay, like if I wanted to do 80% by 2050, how would I actually be able to get there? So the way that you do that is you can construct a business as usual scenario, and then you can construct a scenario in which you meet your end goal. In this case, this is slightly different. This is thinking about solving a particular climate issue. So this is hitting like a temperature target based off of projected emissions by some amount of time. And so this is your sort of default state, and then this is your end state. And so the idea of the stabilization wedges, which is kind of specific to problems of this context, is that you can introduce specific mitigation measures. Like, let's say, okay, what if I have a policy to increase the adoption of electric vehicles? What if I have a policy that requires renewable power deployments? And so what I can do is I can figure out how much each of those mitigation options would decrease the emissions from your business as usual. And so you have this thing that's known as a stabilization triangle, where each measure brings you down to the next sort of line. And so this is a nice sort of way of showing, hey, like if I do these three things, that's going to bring me down here. If I do, all of these things, that's how I can eventually get to my end goal. And so this is a way of kind of like splitting into these manageable pieces. And this type of thing is I found really compelling for stakeholders, because they can easily see sort of a visual impact of how much of a difference a specific mitigation option is doing, how it contributes to your goal as a whole, and relatively how much more is needed to hit your target. So this is not really like a typical projection, right? This is more kind of like a backcasting. And so you start with a goal, which is to stabilize emissions, and then you figure out what actions can be used to meet that goal. It doesn't really care about costs. And particularly in this context, it's just saying, okay, if I do this, like what happens to emissions? So in that particular paper, there were one of the nice things about these types of approaches is you identify a whole bunch of options that you can do to make these wedges. Okay, and so what are those? Some examples of those options are demand efficiency, improvements in cars and building energy efficiency, demand technology, demand reduction, supply side efficiency, supply side technology, and non-energy issues or items. And sometimes this type of thing can make certain policy mechanisms more palatable for policymakers, because often when you do these approaches, like these wedges are not going to be the same in terms of like resources and cost, right? So it may be a lot easier to do, okay, I'm just kind of throwing this out there, It might be a lot easier to do efficiency than it would be to do like demand reduction. So, you know, maybe it's easier to improve fuel efficiency than it is to get people to drive less. And in that way, you can say, well, you know, look, if you do this, if you pursue this type of thing, you're still going to get this benefit, and look, it's going to be a lot easier than this other wedge. And so in some ways it can make certain decisions easier to pursue politically. So the value of wedges. So this context is primarily to address climate change, and it really helps to frame the problem for policymakers. When we think about climate change, right, that's like one big overwhelming problem, but by doing these wedges, it helps to break the problem down into these manageable chunks. Again, it's a simple approach, but can have a big impact. Yeah, and so one of the interesting things that is talked about with these wedges is over the years, things that are sort of more reasonable today than they were, you know, a decade ago when this concept was first introduced. And I think that there are a lot of systemic changes that makes certain wedges maybe a little bit more compelling than they used to be. Okay, so some calculations are path dependent, which can break down some of the wedge analysis. So if the wedges are not independent, in other words, if they're correlated with each other, then the order in which you do the mitigation might matter. Particularly for path dependency. So in this example, like transportation, activity, and efficiency, I can cut activity by 50%, and that reduces emissions by 50%. But if I cut both energy intensity by 50% and activity by 50%, you're only reducing the second half of that by 50%. And so that's a 25% reduction from your baseline. And so in some ways, you do have to be careful in these types of analyses, because the way in which the wedges stack, either in order or if the mechanisms are not independent, can make a difference in what it means for your ultimate emissions outcome. So this slide is more of kind of a warning to think carefully about any interactions there might be between mitigation options in your wedge analysis. Okay, so complex versus simple models. I think this is just again highlighting some of the things that I've been mentioning throughout the lecture. There's this sort of famous quote: "All models are wrong, but some are useful." So simple models, like the ones that we've sort of covered today, can tell a sort of powerful story. They're very transparent, and they're easy to construct and understand and implement and update. Complex models are able to incorporate a lot more details and specific processes, and that can be a really good thing if you need those levels of detail. But there is this, and I think that part is kind of intuitively obvious, but the idea about transparency is really, I think, a crucial one, especially when you talk to like policymakers and regulators. if it's too complicated and you've got this sort of black box, in other words, it's like a model that really only you understand, it can detract from the sort of attractiveness of the model and understanding what it is that's actually driving the results, which in the simple models is really obvious, right? Because you're altering so few parameters at a time. Yeah, so I have this nice little comic version of this slide. And so sometimes it can be better to have a simpler version. Okay. Simple analysis can be particularly useful for policy and for communicating ideas. Very rarely are you ever going to sort of accurately predict the future. And so to that end, making the transparency available and seeing what sort of parameters are useful can be really beneficial. And to the extent that there's a lot of uncertainty in the model, if the uncertainty swamps your precision, then simple models that are can be just as accurate as complex models, because you don't get the benefits of the higher precision with more detail due to the fact that there is a lot of uncertainty. And so that's an important principle to remember, is that you can get into all this really rigorous detail in like an engineering-based model that ends up not being necessary due to uncertainty in other aspects of the system. And so one example that comes to mind, so if I were to think about the fuel consumption of a population of vehicles, one way I could do it is I could just go and multiply the sort of average fuel efficiency, right? Like the sticker efficiency that you might find for a whole bunch of cars in this population by some average amount they drove, and then figure out the sort of gasoline consumption, right? You could do the same thing in a more vigorous way where you can figure out you know, exactly how the engine is operating, right? And you can get into like highly detailed engineering representations of the fuel consumption into how it turns the wheels of the vehicle, and you can figure out like the coefficients of friction for the tires of all of these vehicles, and do that across the whole population of vehicles to get at a really sort of precise number. But that number would get swamped by uncertainty in like how aggressively the car is driven by a driver or the terrain that the car is going on. And so you lose all of the like engineering precision due to uncertainty in other sort of forms. So at the end of the day, if I were to decide on doing this like average fuel efficiency approach versus this like highly engineered approach, you know, it just because it's more complex doesn't mean that it's going to be better, because you lose a lot of that precision in uncertainties in the system. So hopefully that example makes sense. And that's a type of thing that you can really see in lots of more complicated system models that end up being not necessary. And that's not to like say you should never do like complicated models, and that's like a struggle that like I've had personally with because I work in a domain where we do a lot of like complex modeling, and oftentimes I have to think about every now and then you have to step back and think, hey, like is all of this like high level detail necessary, or can we do this in like an easier way? Yeah, and so thinking about limitations and uncertainties is really important to help scope how simple or complex your model needs to be. Okay, so I think I'm actually going to stop here for today. I think this is a good ending point because otherwise we'll be diving into stock turnover models with just 10 minutes left. And what I'll do is we'll move the end of today's lecture to next lecture, and we'll start off with talking about stock turnover models. So I'll end here and I'll just do another reminder again. Homework's due today at the end of the day, and project proposals are due at the end of Friday. And make sure to reach out to me about your proposal before you submit it. Yeah, other than that, I'll stick around for a couple minutes for any questions or comments. Otherwise, I will see you guys on Monday.